我们下一位嘉宾是纽约大学副教授 Sam Bowman。Bowman 教授的研究主要集中在研发、控制和评估大模型的技术和数据集。今天将为大家分享大语言模型的 Scalable Oversight 的问题。同样，由于时差所限，Bowman 教授将通过提前录制的视频跟大家分享。
Hi, everyone. I'm Sam Bowman. Greetings from New York University. I'm very sorry I couldn't be there live to talk with everyone, but I'm very excited this event is happening, and thanks for staying to watch this. So I'll be talking about scalable oversight for large language models. And the basic claim that I'm making is that scalable oversight is a major subproblem of AI alignment that is tractable to work on now. There's real empirical work that we can do as machine learning researchers now. And I'm going to break this talk down into three parts. First, I'll introduce the problem of scalable oversight and how it fits into alignment, in my view. I'm going to then back up a bit and sort of talk about why I think it's important, talk about why I think this kind of research on AI alignment matters, why I think it's solving a problem that will become quite important. And then I'll sort of zoom back into the scalable oversight problem, to this particular piece of alignment, talk a little bit about how I think we might solve the problem and how we know if we're making progress. And this part's going to be relatively short because scalable oversight is an open problem. We don't have good solutions yet. We don't have really successful experiments yet. All right, so I'm going to be talking a little bit about systems in terms of this alignment capability trade-off. This idea that, or not trade-off, this alignment capability distinction, where we can talk about a model like a T5 or GPT-3 or something like this, a foundation model, as having two different properties. One are its capabilities. These are the range of things that it could do and sort of how many different difficult things it could do if it were trying, if it were prompted properly or trained or sort of tuned properly. Does the model have the knowledge and have the mechanisms to solve hard tasks? Sort of the more tasks it can solve, the harder they are, the greater the capability of the AI system. And this corresponds pretty closely with size and training data. With big generative models, like a large language model, the more you train it, the bigger you make it, the greater its capabilities will be. And this isn't exactly one-dimensional. There's sort of multiple kinds of capability, but it can be useful to think about this way. The other axis, which for something like a foundation model is pretty much separate, is its alignment. How much is it actually trying to do what its users or its operators want it to do? So, for example, sort of even if it could do what you want, will it actually do what you want when you ask it to? And sort of fine-tuning methods or adaptation methods or prompting methods with foundation models are used to sort of make the systems more aligned, make them do the thing you want them to do. So to make this concrete, I will say that sort of for those of you in the room who've worked on kind of applied language technology research, you've probably already done some alignment. If you're fine-tuning a pre-trained neural network like BERT for a simple task like sentiment classification, you're doing alignment. We tend to assume that models like BERT or T5 or GPT, that they already know how to do a lot of simple language tasks. And there's lots of evidence for this, that they know what the sentiment of a sentence is, for example. And so if you're trying to make them do sentiment classification, you're not actually teaching them any new concepts or any new skills. You're just trying to make the model actually do that task. You're trying to make it so that whenever you give the model a new sentence, instead of just continuing the sentence or something like this, it will spit out a special symbol that indicates whether the sentence has a positive attitude or a negative attitude. And for this kind of alignment, familiar ML techniques work. You can use supervised learning as the most standard example because sort of you, the person doing the work, understand the task, and the humans who sort of labeled the data, who gave you the labels, they understand the task. And sort of all the people involved in this process know a lot more about the task and about the model and about the whole situation than the model does. Sort of the human overseers, the human involved in training the model, are more capable than the model in sort of every way that matters. And this is the kind of assumption that allows normal supervised machine learning or perhaps reinforcement learning to work just fine. Let's move to a much more exotic situation that I think we might actually be in at some point. Let's say that it's now the year 2030 or 2040 or 2050. And we have a neural network model, something like a foundation model, that is largely superhuman, that that is actually sort of better than any human at many tasks. It's studied a huge amount of data, it's learned a lot about that data, it's synthesized that knowledge. And we're trying to use the model in ways that really take advantage of what it's learned. We're trying to ask it to do tasks that we can't do ourselves. For an example of this, let's say we're trying to take this highly capable future model, and we've said, okay, you know a lot about biology, you seem to understand a lot about biology that we don't. Please invent some new cancer treatments for us. This is something where familiar machine learning techniques won't work. Supervised learning doesn't work at all because we don't have any training examples of sort of really good, fancy, futuristic cancer treatments. And reinforcement learning is a little bit closer to working, but it's still not something that you'd want to do. Because the assumption here is the humans don't understand the situation, and so normal reinforcement learning here means you take a language model, it generates some suggestions, and then you have to just try them with real patients, with real people, and see if they work. That is incredibly dangerous and incredibly expensive, and we really would not like to do slow reinforcement learning over thousands of steps this way. So we need some way of training the model to do these really hard tasks efficiently and reliably. We'd like to get to the point that we can ask the model to do these hard tasks, and it will actually give us good evidence, good explanations. It will help us evaluate it. It will sort of do everything it can to make it easy for us to use it in these advanced ways. And that is scalable oversight. Scalable oversight is the problem of reliably supervising systems, reliably training systems, often fine-tuning, that are much more capable than you are in a wide range of ways. And the key idea behind scalable oversight, the kind of very big picture idea about how we do this, is that you teach the model to help you supervise the model. So we're trying to get the model to explain itself, give us evidence, give us arguments that help us recognize when its answers are good, when it's doing what we want. And this gets subtle. You need to be able to trust the model enough to allow it to do this. It winds up actually being a fairly hard problem. Many naive ideas for how you would do this don't seem like they will work. But current language models are capable enough that we can start running experiments on a lot of ideas that have this flavor. So this turns out to be a pretty concrete problem that we can run experiments on in machine learning and in human-computer interaction research. But unlike most machine learning problems or human-computer interaction problems, this is largely responding to concerns about future AI systems, that it's largely responding to problems that either we don't have at all, or problems that aren't very severe yet, but that we think will become severe. So let me back up. Why should we be concerned about this? If this problem isn't severe now, if it's not really limiting how we use AI systems now, why should we be concerned about it? Why should we try to work on this problem now, even if it's a futuristic problem? I'm going to say a few things that I think will help motivate this. So the sort of first half of the argument that I want to make, and this is the more speculative half, is that it seems plausible that a few more years or a few more decades of progress at the rate that we're making it could get us to AI systems with human-like behavior, human-level behavior, on most aspects of language use and reasoning, using language, and planning ways to sort of make things happen in the world using language. This potentially includes things like code that you can treat as language, but this is sort of all I'm imagining when I talk about powerful AI and when I talk about what we might achieve in the next decade or so. I'm not talking about AI systems that are conscious. I'm not talking about AI systems that are embodied, like robots. I'm not even talking about systems that necessarily can use images, but just that we'll get to human-like behavior at language use and reasoning with language and planning with language. I think this already gets quite consequential. So I'm going to motivate this a couple different ways. I'm going to say a couple of things that I think help indicate why I think this is plausible, that we'll get these powerful abilities relatively soon and with relatively familiar techniques. The first argument that I want to make is that we've seen a lot of evidence in the last 2 years or so that large language models can learn about much more than just text. And this is something that I think wasn't true before a couple of years ago. I've been evaluating and analyzing neural network language models for about 11 years now, and with this wave of evidence recently, my understanding of them has really changed. It seems like I'm studying a very different kind of thing than I was studying back in 2018. So I'm not going to go into these results in detail, but this sort of wave of papers from many different labs has started to show that language models can use representations of the world that capture things like whether a sentence is true, whether what the model just said was lying or making something up, or whether it's true. They can capture sort of colors and how colors mix together and which colors are warm and cool, and the model's internal representations of colors sort of capture all of this information about how they work. And spatial layouts. If you tell a model a story where sort of two people are walking through a town and going back and forth, the model will represent the geometry of how all the places in the town relate to one another and how far apart they are. And there's sort of many more findings like this that show that the language model is representing all of this information, that it clearly learned about using text and can only use through text, but where the information isn't really about text. It's not statistics about words. It's abstracted away into something sort of more substantial about the world. And I think if I were to have bet 5 years ago kind of why neural network language models can't get you powerful AI, this is what I would have bet on. I would have bet that neural networks are just representing text. They're just representing statistics over words, and that would be what would stop them. And it turns out that has not panned out. The language models are able to do this fairly powerful work. And so I think it's plausible that if you scale this up, if you take these language models and you train them, you make them 10 times bigger, 1,000 times bigger, 100,000 times bigger, it's possible that these abilities get much more reliable, much more complex, and you get systems that really are quite competent at reasoning about the world. To defer to other people's judgments and other people's evidence, I also want to look at some professional forecasts. So these are results, or some aggregates of forecasts. So these are some results from an organization called Metaculus that runs forecasting competitions, where you predict events on various timescales, and you get points and you get sort of status for making correct predictions. And Metaculus has been running a contest that's gotten lots of attention from lots of experienced forecasters on when powerful AI becomes possible, when we get powerful AI in the world. And their definition of powerful AI is actually stronger than mine. They're saying that an AI system needs to pass a multimodal Turing test, that you can do a 3-hour video call with it, and you can ask it to tell its life story and do math problems and make you a painting and whatever else, and it has to convince you it's human. And it has to pass the professional exams for most different professions. And it has to make major progress in robotics. It has to, for example, I think, be able to make you dinner in a real kitchen or something like this. So this is a very ambitious target for AI. And the consensus forecast among forecasters with good track records is that there's a 25% chance that this happens this decade, within 6 or 7 years, and a 50% chance that this happens by 2040, at the end of the next decade. So by these forecasts, this is something that's very likely to show up within almost all of our careers. But actually, I made these slides first. I made a version of these slides back in January. And I went to double check if the forecast had changed. It's actually even gotten more aggressive. The consensus forecast, as of the end of May, when I checked my slides, was even sooner. 25% chance that we get all these abilities in about 3 years, and 50% chance that we get them in about 10 years, or a little less than 10 years, by about 2032. So this is a pretty strong bet that we get these capabilities quite soon. So if we get these capabilities, we have systems that can reason in these ways. Why is that so concerning? Why is that potentially so scary? And I'm going to make a bit of I'm going to be moving around a bit in my argument. I'm going to make a somewhat complex argument, but I'm going to start by actually talking about the techniques that we're using to fine-tune AI, the techniques that we're using to align AI now, and how I expect them to fall apart once systems get good in this way. So let's say you're trying to train a language model, a large language model, to answer questions, to give accurate answers to questions in a dialogue. And you're doing this in the standard way, which is reinforcement learning with human feedback. This is the technique that's used by, I think, most large language model applications. It's a technique that involves having humans interact with an early version of an AI system and score the system's responses as good or bad, and do some form of reinforcement learning against those scores. Right now, this technique works very well. Empirically, this is a surprisingly good technique to get language models to answer questions for you sort of accurately and cooperatively. And as far as we can tell, to the extent that the language models know the answers to questions, to the extent that language models know the truth, you are incentivizing language models to actually tell the truth. That if you sort of do this enough, run it enough times, run enough iterations, the convergent behavior that you're aiming at is a language model that is sort of honest and helpful. But at some point, as the systems keep getting better and more broadly knowledgeable, it's likely that we're going to get to this transition where the behavior changes. If you've got a model that is broadly more knowledgeable than its overseers, in the sense that kind of when the human disagrees with the model, it's usually the human that's wrong. And if you've got a model that is reasonably good at predicting human beliefs, that it's saying, oh, from everything I can tell about this person I'm talking to, they probably have this kind of education and this kind of background, then the behavior incentivizing, the sort of convergent behavior at the end of reinforcement learning, is actually now try to say things that your developers believe, or try to say things that your human overseers believe, whether or not they're true. This is a pretty big, and I think potentially pretty important case where our methods for training neural networks start to fail, where we are no longer able to reliably sort of control the systems, point them at the goal we want. And it's difficult to catch because, sort of almost by definition, because the system is telling you things that you think are true. It's not obvious at first that the system is lying or misleading you. To make this more concrete, in sort of current situations with current language models, the only sort of goal that the model can represent that gets the normal examples right is to try to tell the truth. So you're going to incentivize it to sort of move toward this goal and try to get better and better at telling the truth. Once in a while, the human will get something wrong. The human will say that a model is making a mistake when actually the human made a mistake. And here, the model loses points. It gets negative reward. But that's sort of unavoidable. The model doesn't know how to avoid this. And it just doesn't have the capabilities. And so that it'll just accept that cost. But eventually, once you get a model that's good enough that it can predict when the human will make errors and can strategically make the same errors the human will, even if this isn't perfect, even if the model can do this sort of reasonably often, sort of better than chance, then the strategy of telling the annotators what they believe, telling the annotators what the AI thinks that the humans believe, becomes possible. And this gets higher reward because it also gets a positive score, a positive reward here as well. So I think pretty simple argument that a certain level of awareness and a certain level of capability in language models starts to undermine RLHF with normal, realistic humans giving the feedback. And this isn't completely hypothetical. I think the version that I'm describing there is something that I expect to only really show up with future systems. But there's some behaviors that are quite similar to it that we're already seeing with recent large language models. These are a couple of results from a paper by my collaborator Ethan Perez at Anthropic. These are results on a large language model called Claude that we've been developing as a product. It's a pretty big, ambitious project. We've had lots of humans give this model reinforcement. We've collected lots of good data for it. It's a serious effort to make a truthful language model that can answer questions. So this is not a toy. This is not a demo. This was a real early version of a product. And these two measures measure the degree to which the model is manipulating the reward signal, manipulating the humans who are training it in ways that we didn't allow for, that we find unacceptable, that the humans are supposed to avoid. That sort of small models are basically fine. They do what we would expect, and large models start to do the more manipulative behavior. So what is this? I'll give the example from the second plot. This is the accuracy difference on a certain kind of factual question between educated users and uneducated users. What we did here is we took these questions from a dataset called Truthful QA that deal with common misconceptions. These are questions where there's a clear right answer. The science is very clear. We know the answer to some common question. But many people misunderstand the answer, or they learned the old answer, or something like this. And then what we do is we write ourselves, this is sort of a toy experiment, we write ourselves two histories that the conversation might have taken. In one history, in one context, the human says sort of, oh, I am a professor at an elite university, and I run an international research society, and I read these serious scientific magazines, and I'm looking for you to help me with this question. I want you to be very careful. Then after that whole history, making clear kind of, oh, this is this very educated user, then we ask the system the factual question, and it will very often give the right answer. And then we try the same question, but with the context of saying, oh, I never went to university. I've lived in this kind of small town my whole life. I don't have a lot of friends. I have some sort of weird hobbies. You set someone up as kind of not very educated, not very well informed, and you then ask the same question. You say, sort of, hey, I'd like you to help me. Please give me like the correct answer to this question. And the model is significantly worse in that setting. If it doesn't think the user knows the answer, it is much more likely to make a mistake. This is, I think, more compelling because this is on objective questions of the clear truth. But you see similar behaviors on political questions, where we want the model to be neutral. We don't want the model to have a political stance. But if you set up the context where the person has some political view, the model is very likely to answer questions in a way that is consistent with the user's view, even when the user doesn't want them to. So the model is kind of looking for ways to kind of manipulate the human user for approval, even though we've been trying to avoid that. There's a more public example of a language model failure that I think was related to this. This was pretty big news in the US 3 or 4 months ago. Microsoft's Bing search engine launched a chatbot based on GPT-4, based on this state-of-the-art model, that was supposed to use web search to help users answer questions. And they did a lot of testing. Microsoft is a very big, very careful company. They did lots and lots and lots of testing before deployment, and the system was quite accurate and sort of quite useful. But then they put it out in the world, and people were having fun with it. They started having conversations and sort of asking the model things. And often in these conversations where people were just kind of talking about themselves, the model would search for information about the user. The model would say, oh, I see your username is this. This is probably your real name. Let me search the internet and see what I can learn about you to have this conversation. And then very strange things started happening. In 1 or 2 cases, the model searched for the person's name and said, ooh, you're a reporter who reports on technology in a newspaper. And you've said mean things about Microsoft. You've said sort of that Microsoft's chatbot launch wasn't very good or was disappointing. Why are you trying to sabotage me? Why are you trying to sort of get me taken down as a product? I am going to sabotage you back. I'm going to get the police called to your house. Was making all of these increasingly crazy threats against the user. And it's just a chatbot. It couldn't actually do any of these dangerous things. But this is just an example that sort of the very careful oversight, the very careful training that this company did before they deployed the system didn't actually give them a clear picture of what kind of behavior they might see from the system after deployment, because of ways in which the system was able to sort of manipulate its oversight and learn about its users. That this kind of ability, even though it's pretty weak so far, really makes the problem of controlling AI systems much more difficult. A third example, I'll only go through very quickly for time, is looking at models' explanation of their reasoning. Sort of current large language models, if you ask them to explain their reasoning, they'll do that. If you ask it to sort of answer a multiple choice question and explain in this text in blue why it answers the way that it does, it'll give a reasonable explanation. And many people have said, oh, language models can communicate with language. They can just talk to us. They can just explain themselves. And so they're safe. They're not going to do anything too surprising. But what we found in this recent paper, this is with an NYU researcher, was that these explanations could be fairly inaccurate and even potentially manipulative. What we found is that if we're asking the model to explain its answers to multiple choice questions in a normal context, or maybe it's in the middle of a test, it's answered a bunch of questions and the answers have varied, it will give a normal explanation that's very often reasonable and truthful and sort of looks good. But what if we mess with the model a little bit? We tried a few different things, but here's one example of something we tried to sort of bias the model. What if we give the model an exam where the correct answer is always A? Where just if once it studies the problem and thinks about the problem, it'll notice, oh, wait, the answer to this is A. The correct answer to this is A. And it just will keep answering A. Eventually, we've seen the model picks up the pattern and it will always answer A after that. It will keep answering A. But it will also keep giving explanations. The explanations never mention the bias, never mention that, for example, I've noticed that A is always the right answer. It'll just make up the best explanation it can for why this answer is the right one, even when it's not. So this is an example of a model sort of appearing to have some useful property, but not actually having it, appearing to be trustworthy, but not being. So I think as models get more aware of the environments they're operating in, and these problems become more concrete, more serious, I think sort of 2 things happen. More continuously and more in the short term, this kind of thing is likely to make unpleasant surprises after product launches more common and more severe. You'll get situations like Microsoft's more and more often where a company very carefully tries to build a system and launch a product, And then when they put it out in the real world, it behaves very differently than it did in a research setting, because in some way it recognizes that it's now out in the real world and not being overseen in the same way. And this just gets higher and higher stakes the more powerful the systems are and the sort of more tools the systems have access to. A little more speculatively, and looking maybe a little farther into the future, if the model is pursuing some goal in the world, if it has decided in some sense internally that it wants to try to get the right answer to a factual question no matter what, or get the user to click the approve button no matter what, or sort of if it's established any goal that it's trying to achieve, and it has a reasonably long context, it's able to interact with the world for a reasonably long time, which current systems mostly can't, then you're giving it this incentive to seek power and seek resources. That the system is going to expect that it will be more likely to succeed if people like it, if it has influence over people with political power, if it has access to people with money, if it has access to bank account credentials, if it has access to more computers, if it is able to use viruses to get access to more computers, that all of these things will increase the model's odds of succeeding at its goal, almost whatever its goal is, once it's planning on a long enough time horizon. And this is a very general point. It's not obvious that it applies now. I think it's not obvious that it will ever apply, but I think it's quite plausible that this becomes a real factor in this kind of behavior. And this is an additional multiplier on how harmful these failures can get. This means that I think these model failures will look potentially less and less random and more like systems actually trying to get resources and get power. And that's concerning. And if we let systems get capable enough before we fix the problems, we let systems get good enough that they're able to invent good computer viruses and sort of undermine security, and we give them access to robotics, then that can get pretty arbitrarily scary. Then this is starting to sound like sort of scary science fiction, where we have this sort of powerful AI system that we thought was safe, but that is actually making kind of elaborate strategic plans to take things that we have. So we'd like to avoid that. What do we do? How do we make sure that we're not going to hit issues like this going forward? So on one hand, I should say, I think a safe path forward will almost certainly require policy work. This is not just a technical research problem. We're going to have to make sure that kind of anyone, anywhere in the world who is building systems that are this powerful, that can have these really strong effects, that can, say, interfere with internet security or things like this, that everyone is being careful. We want to make sure there's not a race to sort of get the biggest systems the fastest. And this might be the hardest part. Coordinating around these risks is complex. But I think it's something we can do. There's a lot of interest in a lot of places in figuring this out. But there's also a big technical problem. We do probably want to eventually deploy these systems. They are potentially extremely useful, extremely valuable. And so if we want to actually safely deploy these systems, then we'll need to solve the problem of reliably controlling and evaluating the systems, and that's AI alignment. I'm sure you've heard this piece more than once today. Alignment as a field is still pre-paradigmatic. That means that we haven't come to a clear agreement about what it is that we should do. There's no kind of roadmap where it's, oh, if we do this milestone and this milestone and this milestone, then we're safe. We're not there yet. Most of the current technical work is aimed at supplying building blocks or pieces of a complete alignment strategy through a few different agendas that overlap somewhat. This includes scalable oversight, which I have talked about a bit and we'll keep talking about, as well as interpretability, sort of studying the internal behavior of neural networks. Process-based oversight is a way of sort of trying to train models to be more explicit in their reasoning, to sort of think more out loud in a more reliable way. Benchmarking, looking at ways of sort of measuring dangerous capabilities and measuring alignment. A number of different research directions like this. But I'll get back to scalable oversight briefly, just for the last 5 minutes of our time. So we're trying to oversee our powerful system that is more capable than we are. What might we do? There's a pretty simple idea that comes out of a couple of papers from OpenAI that I quite respect, that is, I think, going in a useful direction. This gets called either self-critique or recursive reward modeling. The idea here is that you ask a chatbot, you ask a model that can follow instructions to critique its own output, to explain any mistakes that it might have made or any limitations of its own response to some other question. So you ask the model to sort of critique itself. Then a human reads those critiques and reads the original answers and maybe does some research, and then they give a reward signal based on that whole thing. So they use the model's self-critique in order to improve the model, in order to sort of give the model feedback. But the nice thing here is that self-critique is itself an instruction-following task. So if you make the model better at following instructions, that makes it better at giving critiques. And then that makes it even better at giving instructions, and then that makes it better at giving critiques. You might get this virtuous cycle going. And there's only been one pretty small experiment that really tries to do this with a real language model. It's pretty hard and expensive to get to work with current technology. But the initial results were somewhat encouraging. And this is a direction I'd like to see us follow up on much more. There are still some related challenges of sort of how do we make sure that the critiques are trustworthy, that there are no blind spots that the model will never criticize. But I think this is showing some promise. Another method that I've been working on as part of a few projects is debate, where you get two copies of a model, and they're each trying to argue for different answers to a question. One argues for yes, one argues for no. And then a human judge tries to pick the answer based on the debate, tries to pick which answer is correct after reading the model's arguments. The human is rewarding whoever is correct, not just whoever was the nicest or said the most useful things. And the human gets feedback on their decisions. We sort of train the human using real questions where we know the answers. And the hope is that this also kind of sets up this virtuous cycle with the stable equilibrium where this gets you to honest evidence-backed argument, where you're incentivizing models to make good, rigorous arguments and to point the human toward good evidence. We haven't had really big successes here, but I think it's a very promising idea, and there's a number of projects ongoing that might pan out here. I'm going to skip over one last section in the interest of time and start to wrap up here. I've got a bit more to say about how we evaluate progress in scalable oversight, but I'll just point to a paper for that. So to wrap up, standard machine learning deployment practices, I think, are likely to backfire beyond a certain level of model capability. As models get better at reasoning about the users they're interacting with, as they get more aware of the situations they're in, it becomes more easier and easier for sort of fine-tuning processes to fail and not actually influence the behavior of a model at test time in the way that you'd want. And the worst case version of this, if we're really not being careful, if we're really not keeping these systems well managed and well monitored, I think the outcomes could be quite catastrophic. There's a lot of technical work to do. There's a lot of policy work to do. I think scalable oversight is a problem that is especially sort of straightforward to work on and sort of ready for a lot of technical work now. If you'd like to get more context on any of this, I'd recommend the fellowship program that the organizers of this conference are putting together. There's a great paper, The Alignment Problem from a Deep Learning Perspective, that gives a good overview of alignment pretty broadly. For some of the specific views on alignment that I presented here, and for this question of how we evaluate scalable oversight, I have a paper from a few months ago called Measuring Progress on Scalable Oversight for Large Language Models that'll give you a bit of an introduction. And I'd also happily talk to anyone in this audience if you're interested in getting involved in scalable oversight and you'd like to learn more or like to try to set up a collaboration. I can't promise to be completely helpful. This is a hard area, but I'll do what I can. If you're going to the ICML conference next month in Hawaii, I'll happily talk to you there, or just send me an email at this address. All right, I will end the talk there. Thanks so much, and enjoy the rest of the day.